Welcome back. So what we are going to do is we're trying to we're going to simulate. Okay, we're going to simulate this thing we just talked about. Okay, between combining means and variances. Okay, so this code below, you can do this. As I told you, this one I wrote it in R. You can write the exact same thing in Python. So no big deal. Okay, it's the same set of code, just a little bit of minor syntax differences. Okay, but let's say we create like an empty list. Okay, this is like an empty list which you're going to do in Python later on. Okay, and let's say we run this thing 10,000 times. Okay, where you create a distribution of for salary 25 at a time. Let's say you get a sample with 25 items. Okay, and you have the mean as 60,000 and standard deviation as 15,000. So that's how you can sort of create a distribution. Okay, so let me just show you what it looks like. Okay, when I take this and when I run this, okay, around, okay, sorry, okay, so you see, you get, if you were to take the mean of this, okay, if you take a mean of this, you'll get around $60,000, $16,000, $60,000. Okay, which sort of makes sense, right? Because you use that mean to calculate with this standard deviation a distribution, which is what you get, and every time you run this, you get a different value. Okay, what did I do? Did I mess it up? Oh, maybe. Oh God. Okay, let me try this again. Okay, I don't know. Okay, round. Okay, this one works. Let me take the mean of that. Okay, so 6199. Every time I do it, it's a different number, right? It's, if I were to do it like 10,000 times, if I take the mean of that, I'm going to get 60,000. Okay, or about close to that. Okay, that's your average and the deviation around it. Okay, so that's what I'm doing here. What I'm doing is I'm setting seed. So when you set seed, okay, when you set seed in that same thing, let's say I set seed to any number. Okay, so just seed, say 25. I can pick any number I want, but once I set that seed, and if I were to say round, okay, the same thing I was doing before, you will see I will get the same exact number. Okay, and that's what I want. Okay, I'll get the same exact number. See this? If I remove the seeds, the thing keeps changing. Okay, so this is like a way to tell the tool that I want the same exact series of data every time I run it, so that I can actually track what is going on. Okay, otherwise you will not know what's going on. Okay, so what I'm doing is for 10,000 times. Okay, I'm changing the seed from 1 to 10,000. Okay, I'm running this thing 10,000 times. Okay, and I'm calculating this thing, and I am calculating the covariance between the salary and bonus. Okay, and I save all that information into this data frame. Okay, and let me show you what it looks like once I run it. Okay, this is what it looks like. So these are all covariants. Some of them are negative, some of them are positive, and so you'll get. Okay, that's covariance. And why do I do that? First thing I want to do is find the one where it's the strongest, because we want to prove when the covariance is high, when the covariance is 0, when the covariance is low or negative. Okay, so the first thing I do is pick the seed which has the highest covariance. Okay, which happens to be this one, 1295. Okay, now I'm going to use that 1295 and calculate the salary and bonus information, which I'm doing here. Okay, and that's what it is. Salary and bonus is 58,742 and 12,222. Okay, that's the average. Okay, Now you're now combining the two. Okay, what I'm proving is when I say combine individual means of salary and bonus is the same as taking the mean of salary plus bonus. Okay, this is what we proved before, right? Ex plus y equals ex plus ey, right? And that's what we are proving now. So it makes sense. Okay, exact same number. Now see, remember this is the highest covariance. This is the highest covariance seed because we picked this seed from this thing which has the highest covariance, see, max covariance. Okay, so we are picking the highest covariance seed. Okay, and we are calculating two ways. First of all, we have the variance of salary and variance of bonus individually. Then we just add it up, assuming the covariance term doesn't exist. Okay, we add it up, we get this value, but that's not the same as the correct way to do it, and this is the right way to do it. Salary plus bonus. Okay, how do we know which is correct? Because remember the formula for adding covariance when you have a very strong covariance: 2 times covariance of salary and bonus, variance of salary plus variance of bonus. Okay, see, this is the exact same number. Okay, so what we are proving is that we are proving whatever we went through theoretically by running an experiment. Okay, so we are running an experiment. And then we can calculate the standard deviation of each salary and bonus. Okay, and now the standard deviation of the combined. Okay, now one thing you will notice, so even with this positive covariance term, if you sum the individual standard deviations, right, so 17,333, 5845, the combined is always going to be less than individual. Okay, and that's very important. Okay, which is what we are going to talk about later on with Amazon versus say Walmart. Okay, now not Walmart as much, but say a brick and mortar store versus an online store. Okay, remember this thing. Okay, so variances add, and the standard deviations of individual components is, if you look at individually and add them up, you can technically never add standard deviation. But if you look at these two standard deviation, if you look at it and compare it to the combined standard deviation, it's always going to be lower than the sum of these two individual standard deviation, though you cannot add standard deviation directly. Okay, so we went through that. So the correct estimate is this, which matches we calculate that variance. Okay, so we use that variance to calculate standard deviation. Okay, right here. Okay, now let's find the seed which has no covariance or as small a covariance, right? So this is what we are doing now for the zero covariance case. Okay, so we do this, we calculate a seed which is as close to 0 as possible, and we pick between these two seeds. Okay, so this one is more close to 0 than this one, so we're going to pick 9767, okay, as the seed, and we're going to extract a new series, salary and bonus, okay, with 25 samples, 60, same mean, same standard deviation as before. Now we combine salary. The most important thing, we are talking about variance here because that's where that covariance term matters, right? When we do salary plus bonus, that's the right way to do it. And when we do it expanded form, even including the covariance term, which we know doesn't exist, we see it's pretty close, right? And this is because this is the expanded form of this, so it has to be close, it has to be exact. Okay, but when we do it individually, salary and bonus, without the covariance term, it still is very close to that because the covariance term is close to 0, right? And that's what we are proving, that when you don't have covariance, when you have these two variables which are independent of each other, right, basically. So we are trying to prove that independence between these two variables makes a difference in terms of whether to include the covariance or not, right? Because between these two salary and bonus information, we are randomly distributing bonus. Okay, so sometimes a guy who makes a lot of money in a company can actually get a very small amount of bonus, or can get no bonus, or can get a huge bonus. Okay, so we're randomizing that. Okay, sometimes a person who is on the lower end of the salary scale can actually end up getting a huge bonus. Okay, so we are sort of randomizing that. Okay, now let's look at so almost matches. Okay, comparing the standard deviation. Again, the standard deviation is a lot lower for the combined as opposed to individual cases. Okay, now let's look at the negative correlation case. Okay, so this one is the negative correlation. We happen to know that the seed is 5831. Okay, and we use that to calculate the means and variance. Okay, and that's the right way to calculate variance. Okay, 16. Okay, and the wrong way is this, because we are missing the covariance term, so it is inflating the actual effective variance, which is actually lower because you have to subtract the covariance term 2 times the covariance term. Okay, and the missing covariance term. Okay, and this is so if you were to calculate the standard deviation the right way versus the wrong way, okay, you will see that you are basically overestimating the standard deviation, which is not good. Okay, because you end up making wrong decisions, wrong conclusions. So you see, covariance sort of helps in sort of trying to understand as to what your overall distribution looks like, and where does it help. I'm going to run through a real application. Okay, and this is the same math for a 3 variable case. Okay, and now we're going to talk about the genius of Bezos in the next video.